Swayam Prabha. Digital India. Educated India.
Okay, so to pictorially kind of represent this, so this is taken from this particular source. So what this says is that, so let's say the red area, the red points actually represents our model. I mean, this is just a pictorial way of explaining whatever I just said. So the left top one is the low bias, low variance model, right? So what does that mean? So that means your model exactly corresponds to the truth also, right? So your H and F are very close, and H also does not vary too much with your data set. It does not overfit also, correct? So which means this is the holy grail. You want to achieve this, but you'll never be able to achieve this unless you know something about how the data is generated in the first place, which in most cases we don't know, right? So the high variance, low bias model says that it's low bias, which means you are close to the truth with respect to the modeling assumptions that you are making, right? So you are close to the red area, but then you are scattered around the red area a lot. So which means you are sensitive to the data set that generates the data. The high bias, low variance model is with different set of data sets, your predictions are going to be not so different from each other. They are going to be clustered in this blue area, but then as a whole, they are off from your red area, right? So they are different from your truth, which is the red thing. So this is the high bias case because the bias is the difference between your F and H, but then the variance is low. The high bias, high variance models are those where you've got both wrong. So you are also overfitting, and then you are also doing a bad job with respect to modeling assumptions, right? So you are also off from the truth. You're also sensitive to the data set at hand. So this is the worst possible scenario. So you either want to be somewhere in the high variance, low bias regime, or high bias, low variance regime. So different algorithms fall in one of these two categories, and we kind of want to balance this somehow automatically, and that's and we'll see one way to do that in the next few slides. So slightly more kind of intuition for this. So if we had to, so any questions at this point before I go on? So yeah, so let's say, okay, so let's say my model, my truth was some sine curve. This was my true f of x. This is my f of x. And then there is a noise, right? Because of which I'm seeing these points. So when I run it once, when I sample 10 different points, these are the points I see, right? So now what I'm going to do is I'm going to fit a model to this, right? So let's say my model was like really a high dimensional polynomial model, high polynomial model, right? So which means I will exactly fit this data. So this is for the test point, let's say. So this is my x star in the test point. So this is what I have fit in my training using my complicated model, and this was my h of x star. Okay. So now I draw another set of samples from the same f of x plus epsilon, let's say, and I get the noise is slightly different. Let's say I get something like this. I get this, right? So now if I try to fit these, okay, let me use a different color. Now I am again using that complicated polynomial to fit this data. So the way I'll end up fitting it is like this. So this will be my, okay, assume that's a point here, right? So this will be my polynomial fit, and let's say it goes like this for x star. So which means my prediction for h of x star is this for the second data set. The truth was the same. The truth was still the f, which this was our f, right? This was our f, which is still the same. But the first time I drew certain 10 different points, I got the red points, and the polynomial that I fit predicted for x star a value here. The second time I did it, I got the green points, and the polynomial that I fit predicted for x star here. So for x star, my predictions are on this line, right? So every time the complicated the polynomial becomes, the variance in this prediction for h of x star increases. So that is why a complicated model will have high variance, right? So, but then the bias is low because this kind of mimics the curve, right? So that way the bias is low. However, if I had tried to fit a linear function for this, right? So I should also do that. So let's say for the same red points, I try to fit a linear function. I might have got something like this, right? So which means my prediction for h of x star would be this. Now if I draw a different set of samples, which happen to be the green points, and I again fit a best linear function for this, I might fit this, right? The prediction for x star is this. So now this variance will not be too much here, right? So this variance, the predictions for x star for different data sets will be clustered around the same point. So the variance is low for this model. However, this model itself, with respect to the truth, is high. The difference between the true curve and what I'm fitting is high, so the bias is high. You get that? So this is a simpler model for which the variance is low, but the bias is high. Whereas the complicated polynomial model, the variance was high, but the bias was low. So now you want to balance these two terms, which is kind of the holy grail of machine learning. So the yellow line model would be which among these four? So where would the linear function fall in? So is it this, the left one, left top, left bottom, or right bottom? The yellow one is low variance. The yellow one is low variance and high bias. So this is the yellow part, right? So whereas the other one, the blue one is what? High variance, and this is the high variance and low bias part, right? So every time you get high variance here, but in this case the variance is low, right? So that is what this is kind of trying to capture. Okay. So any other questions in this at this point? So what I want you to understand is this is a fundamental trade-off in machine learning. So right now we have seen this for the regression problem, right? So this is not just restricted to the regression problem. I just proved this for the regression problem by taking the mean squared error and then decomposing it as a sum of three different terms: bias, variance, and irreducible error, and so on. However, you can do this for classification as well. You can do this in an unsupervised fashion as well. If I remember, there was a question yesterday about somebody asked dimensionality reduction. How do we know if we are not losing information, right? So basically, it's the same thing, right? So it's you may want to do reduction in dimensionality because you want to remove this noise, right? So the noise might be leading to a lot of variance, and you want to remove the noise. So it's the same idea. Basically, you want to balance the bias and the variance, and based on that you choose. Okay, so let me go ahead. Okay, so before I say underfitting and overfitting, there's another small thing that probably might be of interest, which is exactly the same thing. So and showing why this is in a more graphical way, why there is a fundamental trade-off here. So let's say the x-axis was our model complexity. So as you go to the right, you get more complex models, and in the y-axis you are trying to, the squared error of the model is what you are trying to plot. So now, how would the bias curve look like as you increase the model complexity? So what would happen to the bias curve? Bias goes down, right? So this kind of goes down, correct? And the variance term, on the other hand, kind of increases, right? So, but what we care about is neither the bias nor the variance. What we care about is the error, right? So, which is kind of the sum of these two things, and it kind of looks like this, right? So, this is like the prediction error. right? So which means now if you want to do model selection, right? So you want to pick a model that kind of balances these two terms, because these two terms are unavoidable. That's what our theorem shows, right? So you kind of want to pick a model which is somewhere here, which has the least prediction error. That's what we want to do, and we'll see one way to do that. So of course, one way you can do that is you can try out different models, and then on the test set you can see which one gives the least prediction error, and then pick one. So there is that means there could be infinite models that you want to try, which does not become feasible at all. So we'll see one way to actually do this in an automatic fashion in a moment. So the degree fitting thing that I already explained. The underfitting is, when does underfitting happen? So in the previous case, so which models will lead to underfitting and which models will lead to overfitting? So in terms of bias and variance, let's say, so if the underfitting models are the ones which have what property? So we'll have high bias, right? So typically the high bias, low variance models are those which underfit, whereas the low bias, high variance model so we want to kind of strike a balance between underfitting and overfitting, when we kind of do model selection. Okay. Prediction curve is something that I already gave. Okay, so one way to do model selection, of course, as I said, you can try out different models and do things like that. So the other way is to implicitly penalize the complexity of the model, right? So for example, so one way to say is, I don't know if I pick a high bias model, which means a very, very basic model, then I might never be able to do well. But what I can do is, I can try to search in a larger space of models, in a complicated space of models, but somehow penalize the models which do not perform that well, right? So in the sense that, so what I want to do is, I want to choose from a large, high variance models or the low bias models. I want to make my model space as complicated as possible, but then let my data decide which model I should pick. In the sense that the complexity of the model should be controlled in my optimization problem itself. So that's what I'm trying to get at. So one way to do that is to see how our model parameters affect complexity, right? So if you remember our standard regression problem that we started off with, we try to do this, right? So we try to do minimize over W 1 to M yi minus W transpose xi squared. So this was our standard linear regression problem that we looked at. And in your lab, I think you guys did by mapping your x to some space phi of x, which potentially is a high polynomial space, and then try to do a linear regression in that case, which means essentially you're fitting a complicated model by mapping your x to a higher dimensional space, right? So that's what you did in your lab sessions, I hope. So now we want to make, let's say we want to make it as complicated as possible, which means this x's, think of this x's as in the feature space that you have already mapped, right? And it is as complicated as possible at this point. Now what you want to do is, in this space you are learning a linear model, all right, which means in the original space you are learning a kind of a complicated polynomial model, but then you want to penalize your parameters in the sense that you want to make sure that your w's are within a smaller range, right? So if you allow your w to be anything, then the sensitivity of the W to a data set kind of increases. So which means I don't have control over how much the W can change with change in the data set. But then if you are constraining your W to fall in a certain area or a certain range in a ball, let's say, then no matter what your data set is, your W is going to fall within that ball only, right? So you're searching your W, you're searching for models in a smaller constraint space, right? So one way to say that is to say that you can make this as a constraint optimization problem and call that you can change your objective to minimize over W such that you have this loss, but then your norm of W is less than or equal to some constant. What does this mean? This just means that W transpose W just says in 2 dimension your W is, if C is 1, or if so this is like a circle of radius C, and your W can only come from this ball, right? So that's what you are trying to say, right? So now you are kind of making sure that your W is restricted to this small space, which means even if the data changes, your W can only change within this ball. It cannot change too much. But then this is a hard constraint, right? So maybe there is a, you want W to change for certain types of data and so on. You don't want to kind of make this constraint really hard constraint. So one way to deal with that is, instead of solving this problem, what people typically solve is what is called as a penalized least squares or a linear regression, which is kind of saying you, instead of making this as a constraint, you add this as a penalty to the, okay, this is just W transpose W, right? So you just add this as a penalty to your objective function itself, right? So now what does this say? So if your W is complicated, so for example, if your norm of W comes from a larger ball, right? So which means this objective function is higher. So which means ideally you want to search for W's which come from a smaller ball. If there is a W which fits your data from a smaller ball, then by all means pick that W. Only if the data requires a W which comes from a larger ball, then you pick such a W, right? So the data will determine what is the complexity of this model that you want. However, now we want to kind of balance these two terms, right? So you are kind of controlling the variance using this second term, saying that your W cannot change too much, but then you kind of want to balance between how much this W fits the model and how much the W can vary. So the way you balance that is by kind of saying you put a balancing parameter here, right? So this is called as a regularization parameter. Now, essentially what we have done is the following. So we have transformed the problem of model selection. You have 100 different models, and then which model to pick, which gives the least prediction error, to a problem of choosing a good regularization parameter, right? So now how do you choose the best regularization parameter? So if you allow that also to be a part of the optimization problem, what will happen? What lambda will get chosen? So let's say I want as low a variance as possible, right? So what I'll do is, let's say I minimize over W and lambda. I choose a lambda which minimizes this. That I could do, right? So if I did that, which lambda will get chosen? The lambda that will get chosen is 0, right? So because any lambda that I choose, this guy is going to increase, right? So this guy is going to give a positive value. So which means I cannot optimize over W and lambda together, right? So in the training at least. So all I can do is, hope for is, I fix a lambda, train the model with that, and then see how much error that it produces on the test set. And then change the lambda, again train the model, and see how much it produces an error on the test set. Correct? And then I can keep doing this for different choices of lambda, and then pick that lambda that will work the best. Of course, that's a caveat here, so I'll come to that in a minute. But so this is the idea. So basically, we have transformed the problem of model selection to a problem of selecting the best regularization parameter. So, and because these cannot be optimized during your training, right? So these are called as hyperparameters. So these are parameters which cannot be part of your optimization routine, right? So these need to be tuned separately, right? So this is what is called as a hyperparameter. So for the case of ridge regression, let's see how this affects our solution. So if you remember, so we in the previous case, if you did not have the lambda by 2 norm w squared, so so you had a half here, if I remember. Yeah. So the solution was analytically derived, right? So we actually derived the solution by taking the gradients and so on. Let's now try that for this ridge regression and see what happens. How does it change from the previous solution we had? So what do you do? So this, you can write this as a function of w, take the gradient and try to set the gradient to 0 and see what happens, right? So let's do the same thing. So what happens if you take the gradient of, so if I call this as f of w, and I take the gradient of this with respect to w. So what happens? So this just becomes sum of I equals 1 to m yi minus w transpose xi into xi plus so let me actually write this down. So I'm just trying to expand this. So this becomes yi squared plus w transpose xi squared minus 2 w transpose xi yi, right, plus this term. And now if I take the gradient, so that just becomes what? So this is 2 w transpose, okay, so that's a half here. So the 2 goes away, w transpose xi times xi minus xi yi. So what gets added? So what is the gradient of this term? So this is w transpose w basically, right? And the gradient of this, think of this as like a into a squared, the derivative of a squared, right? So that's like 2a. So it would be similar to that. So this will be like 2w basically, and we multiply. So this is lambda, sorry, this is then just lambda w, right? So you get this extra term and then this becomes 0. So now if I do the jugglery, so then what happens is this becomes w transpose sum of 1 to m xi transpose, that's a matrix, plus lambda w equals sum of 1 to m xi yi. So it looks very similar to the previous case, except that there is this lambda w that has gotten added. So now if you just try to solve for w, right, so this is w transpose 1 to m xi transpose plus what should be this? What is the extra term that gets added here because of this? So if I am taking w common out, what should I add here? So this is a, what object is this? Is this a number, matrix or vector? This is a matrix, right? So what can I add here? I should add a matrix, right? So only matrices can be added. So what matrix? So if I take w out from this, right? So what is the matrix that gets added here? Lambda? Sorry? Lambda into I, that's correct, right? So this is an identity matrix because this w can be seen as like w transpose I, right? So it's exactly, the solution is exactly the same as before, right? So your w, the analytical solution, is just sum of I equal to 1 to m xi transpose plus lambda I inverse into sum of I equal to 1 to m xi yi, right? So in practice, it's often the case that if you choose a lambda properly, so this matrix will actually be invertible. So so you won't really suffer from the problem of pseudo inverse. You can actually put an inverse here and it will still be okay. So in the tutorial session, we will see, so we saw that if you did not have this lambda I, how this can be related to a maximum likelihood estimate of a Gaussian noise. So I'll let you think about this before the tutorial session. See how this type of W can be related to in a generative fashion. What can you say about if you wanted to think of your Y as being generated in a certain fashion? How can you come up with a solution like this? Is there an equivalence? So that is something that I'll let you think about later. So okay, so this is one type of regularization that we saw. which is called as ridge regression. This is an L2 regularization. The L2, because this is an L2 norm that we are trying to regularize. You are trying to regularize the parameter space W L2 norm. So other way to regularize is what is called as lasso. Which is again, you want to minimize W, which is 1 to m yi minus w transpose xi squared. This is the same thing, but then instead of the L2 norm, you minimize the L1 norm, right? So where W1 is just sum over I 1 to d wi, right? So it is an L1 norm that we are minimizing instead of the L2 norm. So it might seem like a trivial change, and you might want to ask why one would want to do this. So it turns out that if you do a minimization using a L1 norm instead of the L2 norm, the W's that you end up getting are sparse, right? So which means there are lots of zeros in the W's that comes as a solution. And why is that interesting is because finally what is our prediction? Our prediction is W transpose X, right? So you can think of your W's as giving weights to each of the features, and if lots of these weights are 0, then it kind of means that you are implicitly trying to find a W which only picks the most relevant features. All the rest of the features are thrown out, they are given 0 values. You only want to work with that small set of features. In some sense, it's also kind of telling you which are the important features that you care about. So, but one might wonder why a small change from L1 norm to L2 norm to L1 norm would end up giving you sparse solutions, right? So what is the reason behind getting sparsity in these solutions? So that requires a lot of understanding of what happens in this optimization problem. It might be beyond the scope of this lecture, but then to give some intuition as to why that might be true, we can look at this picture, right? So this is sourced from the PR, Pattern Recognition Machine Learning book by Bishop. So what does this picture say? So on the left, you have a picture corresponding to the L2 regularization. On the right, you have a picture corresponding to the L1 regularization, right? So let's say we started off with a case where you did not have a regularization at all, right? So you just solved the least squares problem, and this was the solution to that, right? So now, for different choices of W, so now your X's and Y's correspond to your parameter space, right? So this is a 2D problem, which means your W is just a 2-dimensional parameter, right? So which means that this is a particular unique solution that you will get if you did not use any regularization, right? So now as you change your regularization parameter, so you might get different W's as your answer, right? So there might not be a single unique W that solves your problem anymore. So maybe your for change different values of lambda as you change, so you might end up with contours like this for your error function, essentially. So now, but what are we trying to constrain? So implicitly we are saying that when you do an L2 regularization, the L2 norm of W should be less than or equal to some constant, right? So that is what we are saying. So in fact, that can be seen from the Lagrange multiplier argument that we spoke about in the morning, right? So the constraint optimization problem can be converted to an unconstrained optimization problem by doing a regularization. So which means if you are doing a regularization, it is equivalent to saying you putting that as a constraint in your optimization problem. So the constraint for the case of ridge regression was that your norm of W2, the L2 norm of W2 was less than some constant, let's say, which means your W has to lie in a particular ball, like this. Now if you are searching for your W in this constraint space, and this is how your error function behaves, then so basically you want to find that point in the ball for which the error function is as small as possible. That is the intuition, right? And it so happens that in this case, so your W star hits here, and this W star's value is maybe in this case like 1, 3 or something. Whereas the way the constraint space is in the case of lasso, which is an L1 constraint, is not a smooth ball constraint, right? So it's a norm 1 constraint, right? So norm 1 is less than or equal to C, which means your absolute value of the first coordinate plus absolute value of the second coordinate is less than or equal to some constant, right? So now you can look at the set of all w's for which this holds, and it so happens that this is just this diamond shaped thing, right? So this is the set of all w's for which your absolute value of w1 plus absolute value of w2 is less than or equal to c. That's easy to see, right? So what is this line? This line is w1 plus w2 is 1. This line is w1 plus w2 is minus 1. This is w1 minus w2, and this one is minus w1 plus w2, right? So the absolute value would just be this. So now if you try to optimize this and look at the contours of the error function and where it hits your w space, so it hits here. And this will be our solution vector. And this vector is what? So this vector is 0, comma 1, whereas this vector was 1, comma 3 or something, right? So which means there is you can hope that if your edges are like sharp, then your w that you will end up hitting will be somewhere in the corners. So I know this is a hand wavy argument, but you can make this more precise and so on. But the hope is that, so because these edges are sharp, so you will end up hitting these corners. And why are these corners useful? The corners are sparse, right? So there are zeros here. So this is a 0, 1. This is a 1, 0. This is a 0, minus 1, the minus 1, 0, right? So the corners have sparse w's. I mean, only w2 matters here. Only w1 matters here, and so on. Whereas that is not the case with the w's that we choose here. So which means if you want sparser solutions, typically the way to go about is to do an L1 regularization. On the other hand, also, if you do L1 regularization, you don't get a nice closed form solution like the way we did for L2, and optimization becomes slightly tougher and so on. Nevertheless, this is the intuition as to why someone would want to do an L1 regularization as opposed to L2 regularization.